my apologies on the technical difficulties, but let's go back in now and continue our analysis. So as I mentioned, this is more visual. So we're looking at a visual comparison between test data and simulation. And we've also interpolated those values onto a surface, and we're evaluating them in 3D. And you can see the areas where we have the blue and the red more or less identical. You can see high agreement, whereas if we look at the area kind of on these lower RPMs, you can see that there's not great agreement. You can see the separation between the surfaces. But that's not really a delta. And if we're going to look at a delta, perhaps the easiest way to do that would be in this environment. So what I've done is I've brought the test data, which is in the upper left, and I have the test or the simulation data in the upper right. Now again, you can see this is just the contour. And qualitatively, we can see that in fact, again at the lower RPMs, and especially around 2000 RPM, you can see that there seems to be some areas where we have poor agreement. So what we can do is to take a look at an analytical difference. Now you can see this is just now the delta between the average pressure experimentally or the average pressure from simulation. And in this context, you can see that there's relatively good agreement. Of course, there are areas, for example, here where in fact there are no data. So when you look at a delta, the delta is in fact the complete value from the simulation. So we really want to stick to areas where we have lots of data, which would be more in this area. So let's assume for the sake of argument that we look along 2000 RPM. And on this plot, which is in the lower left, what I've plotted here are the data. The pink line represents the simulation data. You can see there's much more regular and more data. And the 2000 RPM test data are this black-gray line. And this blue line represents an analytical delta between the simulation and test data. And here's 0. So in principle, close to 0 would be an ideal comparison, whereas perhaps if we look at data where we have either large or small deltas away from 0, that's where we have poor agreement. So in principle, just by eyeballing this line, you can see that in this area we should see very high agreement. If we go up here, you can see that's close to 0. And at this point, we have a crossover point, so that's 0 as well. As we get into the lower average pressures in this area, you can see that there is significant differences between those values, and you see here's that negative. So what we're showing basically is we can look at an analytical comparison, this is point-by-point comparison, between simulation and test, as well as the quantitative information. And that's really, when you think about how to evaluate a system, having access to both the quantitative and qualitative information allows you to make a better overall comparison, at least a more scientifically relevant one. So that's what it looks like if we look at more quite simple test and simulation. Let us quickly take a look then at data which is not test. So let's go back here very quickly into PowerPoint. So we've shown then that we can answer that question by looking at the data here. So here's one of the challenges now is what do we do when we have more computational results and we're looking at comparing simulation data. Now in this case, for example, this is a group at BYU that was building a car for a salt flat race, which is basically, it's the Miracle Mile, or the 1.6 kilometer, I guess maybe a better way to think of it. And they basically have 3 kilometers to get up to speed, and then they go for 1.6 kilometers, and at the end of that 1.6 kilometers, they clock the overall top speed. And the goal was to try to see if they could make the world's fastest electric car. And so this was their design. Their design group was looking at 2 designs and trying to figure out, well, what will ultimately yield the lowest drag, and therefore perhaps we will need a little less power. And so 2 designs were evaluated, and they needed to know as soon as possible. So let's now take a look at a comparison of those data. So in this case, I'm going to look at a simulation comparison, and let's start with the 2 solutions to begin with. Now, these data are a little bit larger, so it does take a moment to load them. And while it's doing that, we'll talk about what we're looking at in terms of the context. The solver that was used in this for these results was Fluent. So it was And you can see that there are two, in this case, two solutions, one with a blunt nose, which you can see here, and one with a more elongated nose. Now, the group at BYU actually used Sculptor to evaluate the geometry morphing, and they were able to take a look, and these are the two designs that they identified as the best potential fit. Again, if we start with a more qualitative analysis, you can see that we can look at the relative pressures in both designs. So if we look at, say, a point right above the canopy, and we'll zoom in a bit so you can see those, you can see that they're pretty comparable. And as we move this closer to the nose cone, you can see that, in fact, there are significant differences between the pressure fronts. Now, one thing that you might want to do is increase the resolution or the number of contour levels you have in the lower values so that you can pick up those deltas more quickly. So I can add in additional contour levels, and again, I may want to show these levels such that we see both the lines in flood, and that'll help me help me understand these data a little better, because now you can actually see the individual lines. So this is one way, but let's talk about that analytical comparison. So to do that, again, let's go ahead and bring up both of those views and look at one that's an actual delta. So let me quickly open that up here. So this is the unified view. So what I'm going to do is take these two models and I'm going to put them spatially in the same environment. What I'm going to try to do is then look at what are the relative differences between the geometry and perhaps look at the delta. So what you see here now, the red model represents the initial design and the gray model represents the final design. And I'll let until it looks like there's a lag in the view here, so if I give it a second to update. Okay. So this green, or the slice is now looking at the net delta between the two simulations, and you can see as we move out into the far field, you can see that there's very little delta, whereas if we move closer to the nose cone, you can see where we have the most significant deltas, which is where you kind of would expect them, so just coming off the nose cone. So this is, again, a nice way to compare them, but it's really not as helpful, perhaps, as looking at a more comparative analysis where we want to evaluate all three designs and the delta kind of in one environment. And again, this is perhaps one of the core challenges we face when trying to analyze data like this. And while this is loading, it should come up in just a second. So what we're looking at in this case is we're looking at the models that we started with up at the top, which is, again, that visual comparison where we're looking at the net pressure difference between the first model and the second model. On the bottom, what we're looking at is the comparative delta. Now we're looking at the delta in pressure on the two models. And you can see that the most significant delta, again, is on the nose cone, which is what was changed. But in fact, what's interesting about this is looking at the actual canopy, that the elongated nose actually decreases the pressure on the canopy as well. So there's, in fact, if one were to evaluate then the lift and drag for these data, you can, in fact, look at what those differences are. Now, I've done that already, and basically what we're looking at is about a 30% decrease in the drag coefficient between these two models. So it's relatively significant. Okay. So hopefully then I've shown you a couple of things here. Kind of the key thing is that comparative analysis is a relatively difficult thing to do, especially given all the challenges with both registration, data, coordinate systems. And you can see that there's many ways to do it, including looking at test data and doing kind of more visual comparison, identifying features and systems that may be changing. And finally, presenting that data in a simple form. So I've shown you a couple of examples of how you can use a combination of both visual analysis and comparative analysis in the same environment to help illustrate what those differences are. So one of the key things I wanted to do at this point was open it up to the audience for questions. And I just saw that, let's see here, we still have 15 plus people here. So at this point, I'm going to open it up for questions. So if you have any questions, you'll notice on the side there is a questions area, so you can just submit a question by typing in the question on the side. And if you do that, it will pop up on my screen. Unfortunately, GoToWebinar does not allow for audio questions, although I can see if that's possible. So let me see. I'm actually going to turn off the muting, so if you have a question, you're more than welcome to go ahead and ask that question now. So you can use the either telephone or a computer, or you can actually just type a question. Okay, there was a question about overall data size. The question was, well, how big are these data? Just to get a sense of, I guess, overall performance. These data, if I go to dataset info here, I forget how big they are. They're not terribly huge, so we're looking at about 8 million elements, so not overly large. There's another question about how did you do the comparison and were the grids the same? In fact, in this model, the grid points were in fact the same. The models are in fact morphed, but point by point, the values were in fact the same. If you don't have that registration, what you do typically is create a mesh that you can use for interpolation, and then that interpolated mesh will then be used for comparison. And from a tactical standpoint, being able to create a variable in Tecplot is quite simple. We'll call this ptest. And if we go ahead and set a new variable equal to, say, 9, we can do that real quick. Now you can see that adding variables to Tecplot is very fast. If I wanted to then look at a delta between the fluids here, and so we have two fluids, which is the first model and the second model, so we're just looking at the actual flow domain. I can say, well, I want to look at, say, V3 from the first zone, which is in this case the fluid, and I want to minus that from V3 of the 11th zone. And now I can actually do a zone-by-zone comparison here. And if I look at just that first fluid now, I'll notice in my contour variables, I actually have a new variable available, which is the p-test variable. And if I show, you can see what the p-test variable is. And I don't know what particular zone is showing. So that just shows you quickly how one can actually look at that delta. I wonder if that's nice. So now you can see that delta on the screen. Okay, other questions before I hang it up here? Okay, well, if there are no other questions, again, I apologize for our technical difficulties. We had some internal network issues that caused us to disconnect and also caused us some problems with getting onto GoToMeeting this morning. We do have a recording of this webinar available online, so for those of you who weren't able to stick around for it, you have an opportunity to do so via the recorded session. Again, thank you very much, and we will hopefully see you at our next event. Thank you.